So I'm going to talk about the process of abstraction and the dual process, which I call specification. So abstraction is going from the specific to the abstract, and specification is going back from the abstract to the specific, because of course, what is the point of doing abstraction if you can't get back to you want to go up the mountain of abstraction and then cross back down the other side to get to somewhere. And I'm going to talk about this in both in kind of good old-fashioned AI and also in machine learning. And I think the text on the workshop webpage also talks about this, the tension between good old-fashioned AI and machine learning, which is, yes, a very old tension, where, for example, the term AI began life as an attempt to distinguish itself from cybernetics back in the, I think, 1960s. I don't remember exactly who was responsible for the term artificial intelligence, but there's some interesting story of how it relates to cybernetics. So just so we know what we're talking about, good old-fashioned AI can mean a lot of different things, but it generally means that you have some kind of discrete, maybe syntactic or symbolic representation of the world and your goals, and you're doing some kind of syntactic or logical inference or discrete search, these type of methods. Of course, this is a huge field, spanning many decades. Arguably, the entire field of computer science is basically an offshoot of AI research. And then on the other hand, we have machine learning. And if you want to make fun of machine learning, the go-to case is this one. But this is actually the extent to which I'm going to make fun of machine learning, because I'm actually going to say nice things about machine learning for most of this talk. But it's this big heap of like linear algebra and statistics and calculus, and you just sort of fudge things until it works. But here's the thing, it does work. So I keep every time I brush my hair, I'm hitting the microphone. So part of what I want to say, my big pitch here is that the tension between good old-fashioned AI and machine learning should not be a tension. So arguably, the single most important idea in computer science is abstraction hierarchies. So the most famous one of this is the TCP/IP stack, where at the bottom you have physics, you have like fiber optic cables, and you have photonic wave packets traveling in fiber optic cables. Then something packet switching, and then something cat pictures. Right, this is a picture of my dad's cat that I took. Just so we all know what a cat picture looks like. And so, and the thing is that people who do networking see this stack as a kind of holistic thing. You need every single step of this. If you remove one, you don't have the internet anymore. Nobody is saying like, oh, we shouldn't have the application layer because packet switching is all you need, or the other way around. Similarly, there's a similar story that happens in programming languages, but it's a little bit more controversial or a bit more recognizable to how people talk about AI, because in programming languages, we have this concept of low-level and high-level programming languages. So I guess everyone knows this, but so low-level language is typically something like C, where you're working more or less directly with raw memory. And then a high-level language, of course, this is a huge range of things, but like back in the old days, these are things like Lisp and Prolog, and now there's like Haskell and like lots of crazy things going on. And yeah, there are flame wars in programming languages where people will say, oh, you shouldn't use Haskell because it's too slow. You should use C because it goes fast. And this is not actually true. the boundary also isn't sharp, right? The boundary between low level and high level is still being explored. Like C++ has recently got a bunch of things like lambda abstractions that push it higher level. Rust is exploring this design space of halfway in between very successfully. But when you use a high-level programming language, you have a compiler, and the compiler translates your program down to machine code, and machine code is what the CPU executes. And so, although there are some people who say we don't need high-level programming languages because we can just write at a low level, those people are just objectively incorrect, so you can ignore them. But if you have a low-level language which has arisen from being compiled, sorry, low-level code, machine code, which has arisen from being created by a compiler from a high-level code, it is easier to understand. Like if you want to debug what your CPU is doing and you have a high-level specification of what this thing is doing, it's much easier to understand. If I gave you the compiled version of like 100 million line code base, you would have no hope of understanding what's happening. But people do successfully understand to some extent what's happening in a 100 million line code base. And nobody really calls it, okay, there are some flame wars about this on the internet. If you go on Hacker News and say like high-level languages are bad, people will take the bait. But most of the time, nobody calls this a tension or a paradox. So here's the thing, in AI, I feel like machine learning basically accepts this, at least on a certain level. Like if you actually look at contemporary machine learning papers, depends on the paper and the author, but people do actually juggle different levels of abstraction. Like if you look at papers about transformer architecture, aka the thing that makes large language models work, they use words like keys, values, and queries. And these come from database theory, which comes from good old-fashioned AI. And you could say this is just linguistic appropriation, or maybe better, that they're making an analogy. But I don't think this is really true. Okay, maybe it's an analogy, but it's a very good analogy. It's like a mathematically solid analogy. Like the transformer architecture really is doing like a query lookup of some kind. The fact that these things are implemented as vectors, matrix multiplications, gradient descent, this type of thing, is kind of an implementation detail. Like it's not purely an implementation detail, and like we're still in this crazy exploration phase where people are just trying all kinds of ideas and people are juggling levels of abstraction. So sometimes you come up with some high level idea, but then you tweak it by doing some like crazy low level vectory stuff. And yeah, we hope basically the category theory provides a mathematical way of making this kind of analogy precise. So machine learning, the reason this works is by a thing called automatic differentiation. So in case you were not aware, like machine learning people have not thought in terms of neural networks in a very long time. Okay, I think some people do, but in practice, people write Python code and they import like PyTorch and they press a button. They don't write neural networks, they write a differentiable program. So what these auto-diff frameworks do, these are Python, usually Python frameworks, which will take the code that you write and they will transform it into a kind of machine learning version. So they do this program transformation where they make two copies of your program, one which is basically the program that you wrote, which runs forwards, and then another one which means that you can stick in a gradient vector on the output end, and it will run your program backwards, and it will backpropagate the gradients back to the beginning of the program. And then this is how you train the parameters. So the reason people do this is so that you can put parameters in your program and then you can train them. And like running a program forwards and backwards, if you were in a good old-fashioned setting, is what Prolog does. This is logic programming. The details are a bit different, but the essence of running a program in different directions is very familiar. Okay. So the way that these auto-diff frameworks work secretly happens because of a thing called compositionality, which means that you can do local transformations on your program. If you know how to do transformation on each part locally, you can stitch them together to get the result for the whole. So you don't need to do any kind of whole program analysis, which is typically very hard. So secretly, this happens because of what in category theory we call functional reality. And the simplest case of this is something that everybody learns in high school, which is the chain rule. So the chain rule is the one instance of functional reality that everybody learns in high school. So in programming languages, we kind of get the best of both worlds, where we write a nice high-level program and then we push a button on a compiler and we get stuff that your CPU can run at trillions of operations per second, and it's all good. And what we partially have, and I'm kind of hoping we can get more of in the future, is that we specify our machine learning systems in a high-level way, which is recognizably good old-fashioned AI. And then we have something like a compiler, and of course, this is where the hard part is. And then in the end, grading descent over row. Yeah.
Could you sketch what such a good old-fashioned AI description would look like for, say, a model that would recognize cat picture?
Now you're asking another question. Yeah, that's of course the hard question. Yeah. Right.
Is it as hard as coming up with a program that recognizes cat pictures without automatic differentiation?
I would hypothesize that it's easier, but I accept that I could be completely wildly wrong on that. It might turn out to be harder because it might be that your human ideas of what a cat is actually gets in the way of the machine figuring out what's going on. This is actually what happens with computer chess, is that going from alpha 0 to mu 0 to whatever is the cutting edge now, the details of the rules of chess were removed at some point, and it just learned the rules itself. Okay, so I just realized I forgot to start my timer. I had a timer and I forgot to start it. So yeah, well, yeah. The question is whether I'll be 5 minutes from the end when you tell me that. Okay, I'm just going to wing it. So okay, it's good rhetoric to strawman your opponent's responses in a slide. So this is the yes part, but this is basically all the stuff, or at least the most important that I'm aware of, stuff that I don't know anything about. So this is hopefully, I mean, there is this thing where machine learning people write their architectures at a high level means that you can explain what the architectures are doing at a high level. And this is the origin of where people say that, for example, transformer is the next token prediction machine. Which is fine, but it's like the wrong level of abstraction for the explanations we want for what LLMs are doing. And it also doesn't give us an easy way to explain what actually the brain system is doing. So there's a whole thing about data here that I basically can't say anything about. You have a data set, some magic happens, you do this. So yeah, the question of this black box problem, the question of understanding what an entire trained neural network or individual parts of it are doing is extremely hard. Lots of people are working on this. There's lots of ideas, but nothing I'm saying I think gives any real insight there. You say, okay, if, like GPT-4 has whatever 20 something transformer like attention layers. I don't know how many attention layers does GPT-4 have. Does anyone? A lot more. Okay. Okay, but if I want to say like what is happening at like layer 27, like Okay. So what about analogies? This is supposed to be a workshop about analogies, but I don't actually have anything to say about analogies. But like abstraction's kind of like analogy, right? So to paraphrase Randall Monroe, analogies are kind of like excuses in that I'm making one now. I have now exceeded the quota of one XKCD reference per talk. Sorry, that's it. There's only two SKTD references. So category theory, as Abel said, is a very successful theory of analogies in mathematics. It kind of does the thing that you want for an analogy. It does the thing that you most want from a theory of analogies, in that it actually makes progress. It doesn't, by abstracting, you are not losing something. You are gaining a productive new viewpoint, which you can then respecialize. And category theory, just in practice, is very successful at this like bidirectional process of abstraction and specification. By chance, this same process is what this talk is about. So there's a kind of level confusion. I'm talking about the same thing both at the object level and the meta level. In category theory, we also have a term for this. It's called the microcosm principle. That the same structures that appear at the object level have a weird habit of appearing at the meta level. It's a mathematical rule of thumb. Yeah, somebody said so. I think Goethe said the first part of this poetry is the art of using different words for the same thing, and then somebody, and I forget who it was. Poincaré, okay. Said that mathematics is the art of using the same word for different things. So that's kind of the idea of analogy in mathematics. So yeah, and this actually worked in practice for me because I started out working in foundations of game theory and microeconomics, and then me and some other people discovered a very strong analogy between game theory and several branches of, originally machine learning, using category theoretic tools. And that's how I got here. Yeah.
Do you also use the Ori?
Sorry?
Do you also use the Ori?
No.
Okay.
I feel like my microphone is clipping a bit. Okay, I keep thinking I hear a clip.
I don't care.
Okay. Maybe it's because I'm standing very close to the speaker or something. Okay, I should stand a bit further away. Oh yeah, okay. Well, I need to stand here to change slides. Yeah, actually, I mean, when I was an undergrad, my interest was AI, but that was at the end. That was right at the end of the AI winter. I was in my third undergrad year when IBM Watson happened, and people were just starting to hack the first shader languages for GPUs, like abuse them to do like computation. Like I sometimes wonder if I'd followed that interest rather than going into this other stuff, where my career would have been different. Okay, so that's basically the end of the introduction, which should be, if I'm timing it correctly, should be about a third of the way through my talk. So I want to talk about a particular mathematical structure with lenses. This is my hammer. My entire career for the last 10 years has been spent looking at things and saying, oh, this is lenses. I use this emoji whenever I say this. So lenses are a mathematical gadget that describes a certain class of bidirectional processes. So these are processes that can run forwards and backwards, but in a slightly specific way. And you can think of them as a kind of structural abstraction of the chain rule. So the chain rule gives an important example of a class of lenses. They also describe a kind of hierarchical feedback, and I'll hopefully say a bit more about what this means later. And yeah, the study, so as a result of the types of topic that lenses tend to be useful for, plus my own interests, I named the theory and practice of this categorical cybernetics. So this was, I looked at this and it says, okay, this looks like a new foundation for a new generation of cybernetics that's like recognizably similar, but also different to what's happening in the 60s and 70s, where the fundamental idea was the feedback loop. But yeah, this is because of the range of fields. This is microeconomics, machine learning, neuroscience, software. This collection of topics should have nothing to do with each other, but we get this like really strong mathematical analogy. And by chance, these subjects look like the kind of things that used to come under the umbrella of cybernetics back in the glory days, back before we had academic siloing. Okay, so what are these things? So, okay, I'm going to start to ramp up the technicality now. So if you're confused, please look confused, and then I'll pick up that you're confused, hopefully. So just like functions go between sets, lenses are things that go between pairs of sets. So you go from a pair of sets to a pair of sets. And so we think of, when we have a function between sets, we think of one as like the input boundary and the other as like the output boundary. So you stick some input in on the input boundary, some stuff happens inside, and then you get an output on the output boundary. Here we have both forwards and backwards boundaries on both sides. So you have something where you stick something in forwards boundary on the input side, you get an output on the forwards boundary on the output side. Then you can stick in an input on the backwards boundary on the output side, because going backwards reverses input and output, right? And then finally you get an output on the output boundary on the input side. So actually, I should use the words left boundary, and I tried to do this. I use the words left boundary and right boundary in order to not confuse. Okay, I don't have a good picture right here. In order to not confuse the words input and output. So there are several different useful intuitions for these things. This is part of the reason why it's difficult, and part of the reason that mathematical abstraction helps, because it removes you from individual intuitions. But one possible intuition is that the forward boundaries are some kind of sets of states, and the backwards boundaries are some kind of associated data, like maybe changes to those states or facts about those states or something like that. Now, so here's the definition of a lens. Do I have a mouse? Yeah. A bit laggy. So a lens going from this pair of sets to this pair of sets is a pair of functions where the first one goes forwards between, so we go from the forwards boundary here to the forwards boundary here. That's just an ordinary function. And then we go backwards along the backwards boundaries, so from y prime to x prime, but we have this additional input. There's additional dependency on the forwards input. So this is a kind of a lopsided asymmetrical definition. There is a definition, yeah. This is
X is a space and X prime is expansion from them.
Yeah. Yes.
Okay.
That was not the original idea, but that turned out to be a large class of examples of these things. Yeah. There's a sheaf morphism.
Because I don't understand one thing again. That you say a lens, the function, with which input has a pair and transforms into another pair. And you say that it's a pair of functions.
No.
I don't quite understand that.
No. A lens is not a function of pairs, it's a pair of functions. So this is not a function from x times x prime to y times y prime. That's the different thing.
I can't really like mathematically translate.
The causality goes differently. So it really is this thing. There's a different definition that turns out to be equivalent. This definition is harder to understand because it relies on a technical definition of this word private, which I'm not going to tell you. But if you get it right and you do a bunch of theory, it turns out to be equivalent. Equivalently, this thing can contain some set of private memory states. We have the forwards thing goes from forwards input, and it gives you a forwards output and writes to the private memory state. And then the backwards part goes from the backwards input to the backwards output, and it reads from the private memory. So, and as long as you're careful about what private means, this is equivalent. And this is inspired by how autodiff actually works. And it also turns out to be mathematically best behaved. So it's kind of win-wins. People think of autodiff traditionally as this like really disgusting, complicated thing, but it turns out that if you abstract it in just the right way, it's really mathematically nice. So there's a few different ways of drawing pictures of these things. I draw lots of pictures. I draw lots of mathematical pictures. And in fact, I have a minor sideline in the theory of mathematical pictures. But this is not that talk. So you can read this, ignore the right-hand side for now. You can read this as a lens going from the pair XX prime to the pair YY prime. So we're going from this boundary, and the arrowheads tell you the direction. So we've got input, output, and then we have, so like forwards and backwards on the left, forwards and backwards on the right. Yeah. And then this here is the private memory. So we have like a function that does this, gives us private memory, and then we read that. So you can actually read, so the process is going from here to here, but the arrow of time actually goes clockwise around this diagram. The order of events that happen is first this, then this, then this, and this. That's the flow direction of the arrows. This version on the right, this is the parameterized version. I'm not going to say much about this, but these are really important in practice. So you have some parameters, and then you get some like parametric output as well. Okay, and yeah, you can compose these things together. So if you have two lenses which with a matching boundary, you can compose them, and I'm going to tell you how to do that. So we have a lens from this pair to this pair, and another one from this pair to this pair. How do we compose them? So we need to get the lens from this pair to this pair. Well, the forwards part, I'm unnecessarily confusing things. I've abused notation by using the same letter to refer to both lens and its forwards part, which is helpful for me and unhelpful for you, I think. Sorry. I wish I had put some subscripts to make this clearer. So the forwards parts are just functions, and we can compose them like functions. So we need to get along the forwards direction from X to Z, and we know how to get from X to Y and from Y to Z, so we can do function composition, right? So if we evaluated some input, we just apply F to it and then apply G to its result. And then in the backwards direction, this is the hard one. So we want to get from X times Z prime to X prime, and it turns out that you can do it. You need to use this formula. So the weird thing about this formula is that it involves the forwards part of F. So, okay, try and picture this in your head. We have an X input and a Z prime input. Using F, we can get a Y. Then we have a Y and a Z prime, so we can use the backwards part of the second thing, get a Y prime. But we still have our copy of X that's there. And we can use that together with our Y prime to get an X prime. Yep. Okay, good. Enough people are nodding that I'm confident that this was an okay explanation. And yeah, this turns out to be an abstract form of the chain rule.
It would be useful to have string diagram.
It would, yeah. I have regrets. I made these slides on the train, of course. Okay, so it turns out that, yeah, ordinary backcrop from neural networks and autodiff actually is an instance of this. I think I won't go very technical into this because this slide gets pretty technical. But if we have I mean, copy is, I'm the first to say that copy is important. I do my best. I do my best work in cafes. So if we have a smooth function, we can get this thing called as transpose Jacobian, which is a linear map that goes in the other direction but has an additional dependency on the forwards input. And the chain rule exactly says that these things are composed by lens composition. Yeah. And by the way, this is an example of what in category theory is called a functor. It says this says that we can turn smooth functions into lenses in this kind of structure respecting way. Okay. So what's the point of this? The point is that you can do, like, there are lots of individual examples of lenses. There's this abstract definition, but you can instantiate it in a bunch of different ways that are overall quite interesting. So one way that you can use lenses is to describe the bidirectional process of abstraction and specification. And specification here can mean a few different things, and I'm going to secretly switch between different purposes for which you would want to do specification. But here on this slide, this is about prediction. So here's the thing. So this lens is going from this left boundary to this right boundary. So the direction of the lens is going to still point from left to right here. So in other words, the arrow of time is still going clockwise this way. So suppose we have just by magic, we have a function that can do abstraction, right? So if we get some kind of observation at a low abstraction level, we can forget some details and get the same observation but at a high level of abstraction. Doing this in practice could be very difficult compared depending on exactly what you're doing. Abstracting from like raw image data to it's a cat is well, now it's easy. It used to be very hard. But at least individually, you can build toy examples of this where you can just write like a few lines of code to do this in some specific text. And it's actually not a coincidence that I made this a black box, because I don't care how this works at this point. I'm just saying that you have some function that will do abstraction. We'll go from low-level observation to a high-level observation. Now, suppose that we are now given a prediction of the next state at the higher abstraction level. We would like to specify, is that the right use of English? To specify, to make more specific. Specificate? I have no idea. We would like to make more specific this prediction down to the low abstraction level, right? And in order to do this, so making more specific is actually harder than abstracting, because when we're abstracting, all the information that we are given all the information that we need. But like if you just say like, I want to get an image of a cat, I want to generate a image data for a cat, you're not saying, do I want a photorealistic image? Do I want a cartoon? Whatever. However, if you have some kind of recent low-level observation, you can use this to guide how you should specify this prediction. So this motivates that you give these functions types like this, that your abstraction function is just a function from low-level observations to high-level observations, and then specification takes a pair of a low-level observation and a high-level prediction and gives you a low-level prediction. Okay, so this is so these two functions make a lens.
So are you able to specify exactly what it means to? No, I mean I don't know. Just take an example of your cat picture. Can you give me the circle for identifying the cat picture?
Yeah, I was thinking I should have had an example like this.
I
have to do this on the fly now.
Would the following be an example? So
I want a picture of a cat, but I want it in the style of Van Gogh. So I give a picture that Van Gogh drew of a tree.
Yeah, that's a good.
So we have an input of a Van Gogh picture of a tree. High level observation is it is a tree. Now give me a cat, and it should predict whatever Van Gogh would have drawn.
Yeah,
cat.
That's a good example. Yeah. So this is the kind of thing that you can actually do with deep learning.
Right. So the cat is an input on that side of the right boundary. Something you add.
So cats. Oh yeah.
This example,
Cat would be bottom right.
Yeah.
Demands that like a user.
This is the abstract concept of a cat, or like text. Yes, this is a prediction that you are given. Somebody predicts to you what's happening here, and then you are responsible for translating that prediction down a level. Yeah.
No, it's just weird.
Yeah.
You also think of this like a confusion model or something, like when you throw in these pictures, then you go to this abstract data representation, and then so you have the generative phase where you just add noise at the abstraction level, and then you go back to
Yeah, so in machine learning, you probably would want to call this your latent space.
Yeah.
So I don't know that this usefully works for this type of thing. I know that this works for baby toy examples that I can write by hand in code. Which is a very good old-fashioned way of doing things. And the point of this is that you can chain these together. And I use the word chain not by coincidence, because we're going to use the chain rule, or we're going to use an abstract chain rule. So if you can modify your prediction up several hops in an abstraction hierarchy, and then you are given kind of a next state prediction or something like this at the highest abstraction level, so these are still black boxes. If you already know how to do this, and you already know how to do this, then you can combine them. And you can combine them in this completely generic way, blend composition. So this is very typical of category theory. It doesn't tell you how to do anything. It just tells you how to combine the things that you already know how to do. But this really works. And if you stack a bunch of these together, you can start to do some like actually slightly interesting things. Again, I wish I had an example, but I don't. Oh yeah, right. So this doesn't actually tell us how to build these black boxes.
I'm curious when you say like, but this actually works. How do you assess that it works?
Okay.
This, if you don't have an example, I mean, I struggle here a little bit, like what it actually means.
Oh, this is when I was thinking about this like 4 years ago, I wrote some code and it did interesting behavior that seemed right. Trust me. Sorry. So actually, this example was the one that I actually ran. Yeah. If in the possibly unlikely event I ever get around to actually writing this down in a paper, I will of course have to be clear about all of this. Oh yeah, so one thing about this is that so I tested this when I did this a few years ago with like handwritten code and like very, very tiny toy domains. But in theory, you should be able to do this for machine learning methods as well. I claim. So that's actually a non-trivial claim that could actually go wrong when we try it. So the closest thing you can come to a general argument that you can always do this is using Bayesian methods that you can actually, so we do have a proof that if these are doing Bayesian prediction, then these do actually compose correctly. Yeah.
So the exact abstraction in this middle layer, for example, may not be the same for forward and backward.
Say again?
The current state at middle abstraction level and next state prediction at middle abstraction level.
Yeah.
These the abstractions themselves may not be the same.
Yeah. Yeah, I'm now thinking that if I'd spent half an hour on this, I could have come up with a good example of this to do with like shapes and colors and stuff. I could have probably come up with a decent running example of what this thing should do. And now I wish I'd done that, but there we are. So a different thing you can do is something that looks a bit like control theory, but good old fashioned. So like I call this qualitative control. So this was actually written up in the book. Yeah. I mean, again, in a toy domain. But here, instead of doing prediction, we're doing basically requests for state changes, aka commands or controls. So so here we're going to say, okay, we have some raw. So this is like a fake toy robot control example where we have a robot which is like turning widgets into gizmos or something like that. And you get some raw sensor data, and then it does abstraction of the state. So using raw sensor data, you get some kind of some useful like higher level description of the state. And then another level up, so this is like a task level description saying, oh, I don't have enough gizmos to build the next widget. And then here I have a high level command like build 10 widgets. And then here I have a kind of medium abstraction level command. So this is like navigate to the place where the gizmos are. And then down here, always have like raw actuator commands where I'm like actually controlling my motors. So again, the structure of these things is the same. So in the forwards direction, we just have functions which tell us how to abstract the states. In the backwards direction, so this is I can turn a command into this level, like navigate to the gizmo shelf, down into raw actuator commands if I also have raw sensor data. So the raw sensor data contains the additional information that I needed to know on top of this higher level command in order to generate a low level command. So, okay, this level I never actually built, of course, because I don't have a robot and I don't know how to program actuator control. But I did actually build two abstraction levels of this. And yeah, so if you have a state at this level, like I have seven widgets and one gizmo, and then I give it a high level command, like build 10 widgets, then I can so again, this gives me the additional information which I need to translate this high level command down into a command at this level.
Because if you already had 10 widgets, you would have to do nothing.
Correct. Yeah.
And I can see it for the last one. Why wouldn't the raw sensor data actually combine it with the lower level command?
So this is okay. So for example, I would need to know my exact position in space,
Okay.
this type of thing. Yeah. So sorry, this is all a bit vague. I hope this is all clear. Yeah, I mean, they have to do different things. Yeah. Yeah. Okay, here's another. I think this is my last very technical slide, I think. check. Yeah, this is my last very technical slide. So, so we can upgrade this to a quantitative version. So here's the thing. I contributed to this book, The Road to General Intelligence, which is a lot of it's about good old-fashioned AI, but I don't actually believe in good old-fashioned AI, at least in the old-fashioned sense. Like I am a connectionist as it would have been called when I was growing up. Which is to say, I like things that work and like GPT works. So this is why at the time, so like 5 years ago, we had this, and some people were very excited, but I was not very excited because I wanted to do this quantitatively so it would actually work properly outside of a toy domain. And this was basically my route to making this quantitative. So let's talk about probability. So suppose we have this. So the technical term is a Markov kernel, but this is like it's a probabilistic function. You give it an input, and it gives you an output, but the output depends on the input probabilistically. So we have the probability of some output given that input. Now, suppose we have so imagine how much time do I have left, by the way? Okay, I think that's about right. So like think about this thought experiment. Imagine that you can just observe the output of this function. You kind of sampling from its outputs. How can you learn about its inputs? Well, if you start from a belief about how its inputs are distributed, then every time you see a sample of the output, you can update your belief of how the inputs are distributed. And Bayes' law is the formula that tells you how you should do this. Okay. And yeah, it turns out that these are also mentioned. So we have a channel that is the forwards thing, it's an output given an input probabilistically. And then if we have an input prior and an observation of the output, we can get an updated prior, aka posterior, on the input side. So these two things do actually give us a lens. I'm glossing over some mathematical details, but it's fine, don't worry about it. Now we can also compose these probabilistic channels together. So if I have a machine that will give us a Y given an X probabilistically, and another machine that will give us a Z, if we give it a Y probabilistically, we can just stick things all the way through the pipeline. Now, suppose that we do this and you just observe the Z outputs and you have a prior belief about how the X inputs were distributed. How are you going to do this? Well, it turns out that if you know how to do Bayesian updating for these two functions individually, you can chain your updates together. So it turns out, I mean, I think writing it symbolically doesn't help very much, but it turns out that posterior of this composite is exactly what you would get if you updated each part individually and then chained it together. So actually we have a paper where we proved this, and it's kind of funny that even among experts on Bayesian inference, this is very, very obscure knowledge. Like most people don't know that this is true, which is kind of wild, I think. I think this should be one of the most fundamental laws of Bayesian probability, or probability in general. We didn't discover this. Like a handful of people knew this, but they can't point us to anywhere in the literature where it's written down. And most people don't know, which is kind of funny. Okay, I'm now going to come down from the technicalities back to some kind of vagaries about AI. So, okay, so I've made some weird claims. The one thing that a scientific theory needs to do is make a prediction, right? Otherwise, what's the point? So here's my big hot take about AI. So basically, every machine learning architecture ever is a series of tubes. It's you give it an input, some stuff happens in the black box and then it gives you an output. So a three-layer perceptron is like that. A large language model is also like that. There might be some feedback. So if you do like LSTMs or something, there's lots of feedback going on, but still like there's an input, some stuff happens, and then the output comes out at the other end. It's a function, right? What this is to say specifically is that if you look at a diagram of the architecture, the place in the architecture where the input vector and the output vector appear are maximally far apart from each other. So my crazy hot take is that this is not correct, and that the architectures that we should be studying co-locate the inputs and the outputs in the same place in the architecture. So because everyone here likes Hofstadter, and I'm a big fan of the ant fugue, I say it should be shaped like an animal. An anthill. Pyramid shape. And like the termite mound. Okay. I mean it's just a pyramid, right? But I'm making an analogy to the ant fugue. So what that is to say is that so this is an abstraction hierarchy, and the architecture is reflecting the abstraction hierarchy. So low level happens at the bottom, and the higher up you go, the more abstract it happens. So you have inputs at this low level, and it kind of propagates upwards in the hierarchy, and then it starts to come down again, and then the output happens at the same level. I am absolutely not an expert in neuroscience, but I understand that there is at least some evidence that the mammalian cortex is structured in this kind of hierarchical way. There's a load bearing question mark here, because then the question of like what if this thing is a pyramid, what's at the top of the hierarchy? I think if you say the word consciousness at a workshop like this, I think of like Monty Python policeman walks on and escorts me off stage. I am not an expert in neuroscience. I think there might be some evidence that long-term memory formation lives up there, but I'm not sure about it.
Do autoencoders have this shape?
No, autoencoders as well. Okay, so autoencoders are still input to output processes, but it's possible that the correct perspective is to fold them in half.
Right.
And if you fold them in half, then they might have this shape. Yeah.
Why do we want to go with why not open the don't or sometimes the rich higher sometimes?
Okay. Yeah. Okay. That's it. That's probably correct. It probably shouldn't be a neat pyramid, but a very complex, jagged shape.
Yeah. Why not the torus? Where schools?
because I don't know how to make a torus in slides. No. What do you mean?
But we will put an output will be continuous going in and out and no start and
So the point is that your input propagates up an abstraction hierarchy until you have reached an appropriate level of abstraction to answer that particular input, and then you come down again.
but the also abstraction change. Maybe was abstract from you and outside and depending for what when I'm then.
I'm about to talk about this.
So then it's like a floor, you can also change what's abstract.
I see. Yeah, I'm about to talk about this. Am I about? Okay, that's 2 slides ahead.
Good, so
Yeah, okay. So, yeah. I'll skip over this slide, but there's a thing that if you can do prediction, you can do control. There's a slightly controversial field called active inference, which is this like weird mixture of probabilistic methods and a bunch of weird statistical physics and reinforcement learning, and it's kind of strange, but I kind of like it. So the fundamental idea is that the command raise my hand is the same thing as the prediction my hand will raise, because your actuators are wired so that if you give them prediction, they will attempt to make that prediction true. And then if you do this, you can conflate prediction and control, and then a lot of these things come into sharper focus a bit. So there's one major, and this is my last proper slide. All of this only works nicely so far if we actually impose the hierarchy by hand. Learning abstractions is very hard. So some people in machine learning are aware of this. So for example, there's a minor subfield of hierarchical reinforcement learning, who I think are doing some fairly cool things, but they've specifically identified that their methods only work if a human is imposing the abstractions that they should be learning. And as soon as you say, okay, here's just a bunch of raw data, figure out the abstractions yourself, nobody knows how to do this in practice. I guess if people knew how to do this in practice, then like maybe these analogical reasoning tasks would be solved. So and the thing is, the Riemannian cortex seems to do this. Like we seem to be learning stable representations at multiple abstraction levels, and probably sequentially, like you learn lower levels before you learn higher levels. Like you rely on the fact that you have a stable representation at a lower level before you can really make progress on learning higher level abstractions. Like you learn to count before you learn abstract concepts of number and algebra and whatever. But another thing I wonder is that so this is more of a crazy idea, I think, but maybe very appealing to some of the people in this room. That can we really get the best of both worlds between good old-fashioned AI and machine learning? Can we use good old-fashioned AI methods to not learn but infer abstractions while still using machine learning to do the computational heavy lifting? Another hard question I have is that like serious question, is this actually what attention layers and large language models are actually doing or attempting to do? I think I'm also not an expert on large language models, but I'm vaguely aware that there is some evidence that that might be what's happening. I think this is either controversial or an active topic of research or both. Okay. I don't need to have my, am I out of time?
Kind of.
Yeah, that's fine. References.
Your question?
Oh, no, not a good sign.
I have a question. So since you draw inspiration from cybernetics, do you know if in the 60s they were thinking about analogies? Because they had analog computers, which are like analogy computers, right?
Yeah, I guess so. I mean, analog computation is a pretty specialized thing.
But analog just means analogy.
Yes.
Yeah.
Well,
Yeah. Yeah. But
No.
Yeah, exactly.
before that, yeah.
They're built as an analogy for something. Yeah. Yeah. They're like a physical analogy. An analogy. So, but were they thinking about it in these terms?
I don't know. Given that it's quite a big field and lots of people are thinking about lots of interesting things, I'm going to make a wild guess that yes.
Right.
But I don't know. It's kind of funny. I'm not actually that knowledgeable on historical cybernetics. It's quite outrageously appropriate for me.
There's also these things about information bottleneck principle in machine learning, which is this idea that as your layers progress, your representation will become more abstract, and then kind of you go back, right? And then you have these features which your model can do. But so I was wondering, why do they have to be in the same space, input and output, right? You have a question where the input and the output give different spaces, and then for machine learning, mostly it's kind of two pyramids, right? So you have your input, then you go, then you can make it smaller, and then you go back up again.
Yeah.
Why is it wrong?
You have a pyramid and then an upside down pyramid balanced on top of it. Yeah. So, I mean, perhaps it's not wrong. Perhaps you just need to see it folded in half. In which case it starts to look like a pyramid.
Yeah, but what's the difference? Well, why is So I don't see that why one would be better than the other.
So this is it's specifically to do with how the information propagates. So in so when you have these lens hierarchies, the information flow is local. So each layer is giving its forward output, but holding on to its local state. And then when the information flow comes back the other way, it uses the local state that it has. So in machine learning, that is used like ubiquitously for backlog. That's how backlog works. But basically what I'm saying is that that kind of idea works at higher abstraction levels as well, at like more conceptual levels. So what's specifically different about the pyramid with an inverted pyramid on top architecture is that for that to match, you would have to be wiring directly the bottom level to the top level and the second to bottom level to the second to top level. That's what this local state would be doing. So when you fold it in half, those become polar things.
But these are also architectures which kind of use all the representations. So there's like a pyramid, and you give the whole pyramid as input, and then you get something back. Maybe that's already kind of like the pyramid. Right.
Yeah,
I think what
I don't know. It was some saying.
I think what you're talking about layering each from the inside to the outside, layering each using the inputs of one representation.
Yeah.
I think those kind of already exist in some sense. Like for example, UNets and these kind of REST like architecture and have information for between the input and the output of the representation. That's moved on.
Okay, that's good. Actually, very slow.
I have some questions about, it's a metadata about lenses. When did it start? How many people are working on lenses? How big is it? How old is it?
It's pretty. So okay.
Internal dates.
Oh yeah, right. Did I not write dates?
No.
I guess so.
Years.
So I've been doing this for about 10 years. Say roughly the last 8 years, all of this stuff's been.
You're the creator.
I mean, and all of these people and some other people. The majority of people on this slide are PhD students or were PhD students at the time. Of course, 10 years ago, I was a PhD student as well. The term lens actually, yeah, there's some interesting history where the term lens actually originates in database theory of all places, and was known for a decade or two in database theory before. So I'm largely responsible for nicking that piece of mathematics and using it for a bunch of stuff that it was never intended for. So the name lens originally came from the idea of zooming in on data.
And how many people are working on it now?
Maybe 20. It's pretty small. It's a niche subfield of a niche subfield.
But they did attract Silicon Valley funding. Wow.
Let's not talk about that. Yeah.
Yeah. I like the part. I actually use towards getting a categorical concept. That would be really cool for the first part.
Turn around and ask Martha about categories of concepts.
Yes. That's why I asked how before.
Yeah.
And I'm curious because it was mentioned that this is a part of light category theory. I can see we are applying it. Do you know about that? It's applied category theory, like this type of name.
So yeah, 100%. So in fact, so because mathematics being what it is, so Spivak works very heavily on these things, polynomial functors, and the morphisms of those, that's what the phrase that will only make sense if you know category theory, are basically lenses. The equivalence is non-trivial to prove, but it's secretly the same thing.
And he started a database.
Yes, but before he worked on stuff that looks anything like this.
Right.
That's kind of a weird coincidence.
Oh,
Okay.
okay.